Hello everyone, my name is Emanuele Giuseppe Esposito, and in this demo I will show confidential containers for financial services on public cloud. How to use Coco and Intel TDX hardware to protect an AI workload on Azure. Secure business in the public cloud. Why is this interesting for FSI? We are going to look at why financial services now consider using cloud computing, which saves costs and allows for growth. FSI compliance. Financial organizations must protect their data according to strict regulations. They have been hesitant to move to the cloud due to these rules. Cloud benefits. Using the cloud can reduce costs. Think of consumption-based payments for special devices like GPUs. In an on-prem installation, such components will need to be bought, maintained, and so on. Also, public cloud services allow for scalability and stay available with little downtime. Confidential computing. As we move financial operation to the cloud, security demands grow. We must strengthen the protection around data and business processes to ensure that even the cloud providers administrators can't access sensitive information. Additionally, current and upcoming regulations mean that the regulators will examine this cloud-based system more closely, especially those critical to the financial system. The ideal scenario for financial services is where compliance, cloud benefits, and advanced security intersect. This area allows them to adopt cloud solutions effectively. Our goal is to show how financial services can securely use the cloud. We will use the example of detecting fraudulent activities by using confidential containers using Intel TDX technology in Azure Red Hat OpenShift. Before showing the demo, let's look what a confidential containers project is and what we are trying to solve. Let's assume we have an AI workload running on a pod on a traditional OpenShift worker node. The worker node is running on the public cloud. What are the attacker threats that this workload faces? First of all, the OpenShift admin. The OpenShift admin has the access and the right to the pod. It can therefore access the pod and our model with its data. The pod workload software. The pod OS, the operating system that is running the pod, is malicious. It can try to spy or manipulate the data inside the model. The cloud host admin. The cloud host admin wants to log into the pod. Because it's part of the public cloud provider, they created the worker node, therefore they have the right to access it. The cloud provides software. The cloud provides software is malicious. This is not a person, but the software itself is malicious, therefore it can try to dump the memory and access what's inside the worker node. Again, they can do it because they created the worker node. How to solve the first, third, and fourth scenario, confidential containers. The idea is that the pod, which becomes a confidential container pod, it's not running anymore on the OpenShift worker node, but it's running on a trusted environment. More technically, what this means is that the trusted environment is a confidential virtual machine that is created and managed by the technology called Spear pods, and it's enabled by hardware trusted execution environments, TEs. So this is enforced and by hardware too. Let's look at the various cases that were shown before. The OpenShift admin wants to log into the pod. This is not possible anymore because the OpenShift admin cannot access the confidential virtual machine, therefore also the confidential container pod. The cloud admin tries to dump the memory content, so physically manipulate the hardware. This is also not possible, meaning that they have the hardware, they can access the hardware, but wherever they access is just encrypted data, and they don't have the key to decrypt it. Therefore, they will not read any useful data. The cloud admin trying to log into the pod operating system. Again, this is not allowed with confidential virtual machines. In the last scenario, the cloud software tries to access the memory content, so the cloud provider software is malicious. Again, what they will get will be only encrypted data, and they don't have the key to decrypt it. To solve the case where the pod OS is malicious, we have another service, is called attestation, which is basically a protocol that makes sure that the confidential virtual machine runs with untampered software, which means that the confidential virtual machine and the confidential pod will not run or will not key the key necessary to run it unless the software has been proved to be untampered, as the memory has not been modified, and the correct CPU state. This is enforced by hardware. Let's look at the use case, the fraud detection. First of all, it's worth mentioning that this is a collaboration between Intel, Azure, and Red Hat. Intel is provided the hardware, the Intel Trust Domain extension, which enables confidential computing. Azure is the public cloud provider. We will run this demo on Arrow, Azure Red Hat OpenShift, a service-managed OpenShift. Red Hat provides their OpenShift sandbox containers operator, which provides the peerpods technology to create and manage confidential virtual machines. And Red Hat OpenShift AI enables the platform to develop, train, and deploy models, AI models. Let's look at the fraud detection. This example is taken from the workshop fraud detection available in Red Hat trainings. This example of fraud detection is just a model that mentors credit card transaction for potential fraudulent activity. It analyzes the following transaction details: geographical distance from the previous credit card transaction, the price of a current transaction, whether the user completed the transaction using hardware, chip, entered a PIN number, or did an online purchase. All these data together are given to the model, and it outputs the likelihood of the transaction being fraudulent. Assumptions. In the workload, in the workbench, we can see there are three different phases. First of all, the development and training phase. This is usually done via Jupyter Notebook, but also pipelines, where we create the model and when we upload it to the second phase. The second phase is uploading the model to a storage, usually S3 bucket. In this case, for this demo, we are using local storage. The model is then uploaded and is available to be deployed. The third phase is model service, the inference phase, where the model is downloaded and run in a separate container. We will assume that the first and second phase are run in a user-secure environment, not on the public cloud, which is assumed to be safe. What we focus on in this demo is the inference service pod. The service pod contains the model, and we want to protect it from access from the public cloud admin software and the OpenShift admin, as shown before. First step where we can improve the situation is to encrypt the model. So the model is developed and then uploaded already in the storage as encrypted. Therefore, when we inference, we can get the key that has to be present in the worker node to decrypt the model and run it. This, however, does not solve any of the cases shown before, because the attacker, as shown here, can still get access to the worker node that contains the key. So the problem is just shifted, because the OpenShift admin can still access the key, the cloud admin can still access the key, and also the cloud software. The solution with Coco is to deploy the key in another service called Key Broker Service, which is the attestation service. Again, this has to run in a user-secure environment. What this provides is a key only if we are running the pod in a confidential virtual machine, and the attestation is successful, which means that all the software running is secure, has not been changed, and is the original one that we intended to run. The confidential VM, as shown before, is enabled by peerpods and the hardware trusted execution environments on the public cloud. To conclude, it's worth mentioning that the fraud detection involves the following operators and companies. Intel TDX provides the TEE, so the hardware. Azure Arrow in this case is the public cloud. The OpenShift sandbox containers provide the peer pods and Coco, and the OpenShift AI provides the model serving. Let's now look at the demo. Let's first look at the Microsoft Azure Web UI. We can see that for Arrow, Azure Red Hat OpenShift, I already created a cluster and called it fraud. The cluster is up and running. Let's log in into the cluster. Inside the cluster, we can see that I already installed the Red Hat OpenShift AI operator that together with the serverless operator and service mesh enable the user to deploy an AI model. The OpenShift Sandbox Containers operator is instead essential to deploy confidential virtual machines and Coco. Let's look inside the OpenShift AI. I created a model called fraud detection and a workbench fraud training. In the fraud training, we will develop and train the model. This is exactly as in the workshop. Let's look at the first stage, the development. So we load the data, we build the model and train it. After we are done with the training, we save the model. Because it's an OpenVINO model, the model will be .onnx. The additional step that we perform at this phase is the encryption, just as shown in the slide. So we encrypt the model and we can see now we have two models, the encrypted one and the plain text one. And as a next step, we delete the model, so we only have the encrypted one. As a second stage, we upload the model to the storage. In this case, it's local storage. We can see that the model encrypted is uploaded to the local storage. We only upload the encrypted one. Let's go back now and deploy a model. We already deployed a fraud inference Coco, which is an OpenVINO model server, which provides also an inference endpoint, so an endpoint where to contact the model. If we look at the pod that is running this model, it's called fraud inference Coco predictor 002 deployment. And if we look on the Azure virtual machine list on the web UI, we can see that in addition to the 3 master nodes and the 3 worker nodes, there is an additional virtual machine called exactly the same name, PodVM Fraud Inference Coco Predictor 2. Additionally, we can notice the size of the virtual machine. It's not the same as the master and workers. Instead, is standard DC16 EDS v5. If we look at these sites to the Azure documentation, we'll see that DC EDS v5 series are confidential VMs, so Azure confidential VMs, and feature the Intel Trusted Domain extension. Let's go back to the log of the pod, and we can see that the pod downloaded the encrypted model. The next step is to fetch the key. As shown before, we need to contact the key broker service and perform the attestation. Once attestation is successful, we can download the key and we use to decrypt the model. Once we are done with decryption, we just rename it because we have an encryptor and we can see also the decrypted file. We rename and run it as normal. What is left for us now is to query the model. We have initially a setup where we decide to contact the fraud inference Coco model, and the REST URL is all provided by the OpenShift AI operator in the previous page. We then have two examples. The first example is not a fraud. The user buys a coffee. The location used in this example is the same as the last transaction. The median price again is very similar. We are using the PIN number and the chip and not an online transaction. The output of the model when we feed this data is that this is not a fraud, exactly as we thought. In the second example, we have a fraudulent transaction. In this case, we have a transaction that is done very far away from the latest transaction because the credit card was stolen. Similar median price, not using the chip and not using the PIN number, and this done through an online transaction. When we feed this to the model will answer that this is a fraud, exactly as we thought. To conclude, confidential containers enable running services in the public cloud in an isolated and secure way, allowing the customer to reduce costs in a flexible way. This concludes our demo. Thank you and goodbye.